Right, question 4, the NMR question. The first few parts were relatively straightforward. First of all, a use for NMR spectroscopy in medicine, MRI imaging or MRI scanners. Right, you could also have said body scanners or scanning of internal structures or for detecting tumours or cancer. Okay, but MRI scanners is what you've met in the course. Right, the region of the electromagnetic magnetic spectrum used, radio waves. Right, now the solvent you actually can buy, which you use in chemistry, is many chemical reactions, is CHCl3, but for NMR spectroscopy you use CdCl3 because the deuterium is not NMR active. Okay, it's got a even number of nucleons, it's H2. Okay, so why do we use CdCl3 and not CHCl3? Because CdCl3 does not have any H atoms, or because we see no peak from the solvent in the spectrum, or it does not show on the spectrum, or to prevent that solvent CHCl3, if it was CHCl3, from interfering with our NMR spectrum of the compound that we are studying. Okay, so relatively straightforward first three marking points. Right, carbon-13 spectra, once again relatively straightforward question. How many different carbon environments? All you have to do is count how many lines you have. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 carbon environments. Right, scary looking question. You have to figure out what the rest of compound L. And now once again, if you just interpret the spectra, say what you have at each delta ppm, whether you've got a triplet or a singlet or a doublet, and what sort of proton that corresponds to, you're probably going to get most of the marks here. Okay, so go into interpreting the spectra. So you got this carbonyl compound, you're not sure what R1 and R2 is. Okay, it reacts with this molecule, 2,4-DMPH, and you make this compound precipitate L. Right, and once again, you're not sure what R1 and R2 is, but here's the NMR spectra for it. Okay, so first of all, go into the analysis, interpreting the spectra. Now, keep it here. Where the question was, well, first of all, use the answer to compound as to part C, and in part C, in the last page, we worked out that this compound has 14 carbon environments. So use that information and the data given to you. There was NMR spectra to identify R1 and R2 in the molecule compound L. Right, and also you're going to use the splitting patterns which you got on your the chemical shifts which you have on the data sheet. You're going to explain that in your answer, how you use them and how you interpret the spectra. Right, key point here was, if you look at compound L, you've got a H on a carbon. Well, actually, you don't see that, but it says where you've got C double bonded to an N, which you've got here, right? And any carbons attached to that same carbon, so it must be either R1, R2, and H is on that carbon. It would have a peak in the range of 1.6 to 2.2. Okay, and so the one peak in that range. Okay, it's that peak, because this quartet looks like it's more towards, well, almost 2.5. Okay, so that there, you've got 3 H's. That must mean, and no adjacent H's, that must mean one of the R groups, let's say R1 for example, must be a CH3. Okay, what else do you have on R2? Well, looking at a data sheet, you've got RCH3. Okay, RCH is potentially going to be a CH3. It's a triplet, so next door to it, you're going to have a CH2. Okay, and if you had a CH2 next to a CH3, the CH2 would appear as a quartet, and you have got a quartet. So where you see triplets and quartets, it tends to mean you've got a CH3, CH2. Right, but what's CH2 attached to? Again, look at your data sheets. It comes almost close to 2.5. Look at your data sheet. So either it's a H on a carbon attached to a carbonyl, H on a carbon attached to an N, molecule. You don't have that, you don't have a carbonyl. And also, well, it could actually be a carbonyl, but also H is on a carbon attached to a benzene ring. It's probably going to be that because, look at your spectra, you have got aromatic protons. You've got 7 aromatic protons. You were only expecting 1, 2, 3. That must mean you've got 4 more aromatic protons. Okay, let's put that down there. And of course, we've also got an NH somewhere. We've only got a peak, which intuition of 1. That must be your NH peak. Okay, so if you've got 4 more benzene protons, that must mean you've got a di-substituted benzene, and on that benzene it looks like you've got a CH2 and a CH3. Okay, so a methyl benzene CH2 CH3. Right, well, of course you're going to get mostly marks just from interpreting the spectra, so go through each peak and say what you have. Also assign the peaks. So gone through the first 3 peaks, just said where they appear. Of course, the multiplicity integration, the triplet means you've got 2 adjacent H's, and it also comes in the region. Look at your data sheet. It is the, again, make sure you look at the right one, so this is proton NMR, not carbon 13, RCH. The one at around 1.8 ppm, that sort of fits this one here. Okay, singular integration 3, no adjacent H's. That's probably going to be a CH3, so one of the R groups is most likely going to be a CH3. Right, and then you've got 2.3, 2.4 ppm quartet, integration 2, 3 adjacent H's, and also you know from where it appears, around 2.3 and 2.4, it's going to be one of these. You know it's going to be a CH. H is on a carbon on a next to a benzene because you have got benzene protons, aromatic protons. Right. If you know you've got a CH3, CH2, you can build up part of the molecule. I'll also mention that. Now, there's no mark for the peak at 1.8 because they've told you in the question what that is. Right, but I'm going to now say I'm pretty confident I've got a CH3 next door to a CH2 before I continue interpreting the spectra. Okay, so we know we've probably got a CH3 as one of the R groups. And also the rest of the molecule, probably a benzene attached to a CH3, CH2. Anyway, keep interpreting the spectra. We've got an NH and some benzene protons. Okay, so that's a singlet, no adjacent H's, that must be the NH that you've got in, that's part of precipitate L. Okay, now you had to spell triplet or quartet correctly for the 3rd marking point. Right, and then of course in the aromatic region you don't need to worry about the splitting patterns, call them a multiplet. That's the benzene protons. Now once again, so we've probably got, it looks like a CH3, okay, because using that information. The rest of the molecule looks like we've got a CH3, CH2 attached to a benzene, right? And we've got 7 benzene protons, 1, 2, 3 in this part of the molecule. That means 4 left over. So the molecule must be, okay, so one of the R groups was a CH3, second R group a benzene attached to a CH3, CH2. Right, now you know the CH3, CH2 is on this carbon because you put it, let's say, there or there, and you count the number of carbon environments, you would have got a different number to 14. So that would have been a bit of trial and error, but with this molecule, you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 environments. That's the only one that fits with CH3, CH2 opposite this carbon atom. Right, now draw compound K. If you go back to the last page, K was just that compound where R1 and R2, which we now know is a CH3 and a benzene with a CH3, CH2 attached to a carbon, and then that was double bonded to a oxygen. Okay, so 1 mark there. It's not a bad question, just interpreting the spectra was the majority of the marks in this question.